everyone, welcome to GemChem. Now today's video is on alkenes part 7 video, and here we will deal with halogenation of alkenes and allylic halogenation. Now before starting, if you have not watched the previous video on alkenes part 6 video, you can watch it. I will give the link in the description box as well as the I button present above this video. Now let us start today's video. Now for halogenation in the double bond, that is addition of halogen to the double bond, alkene is treated with chlorine or bromine in inert solvent to give an addition product which is known as vicinal dihalide. Now this inert solvent which is being used may be chloroform or CCl4, that is carbon tetrachloride. Now this reaction proceeds via the formation of cyclic halonium ion and followed by backside attack, that is SN2 reaction. Now energetically favorable but entropically unfavorable process is halogenation, and at higher temperature highly unfavorable, and in that case substitution is more preferred to occur than addition. We need higher concentration of halogens to shift the equilibrium towards the right side. Okay, so see this one, this is a double bond present, and on addition of X2, that is a halogen, whether it is Cl2 or Br2, we get a product, and we see that the two X are present in two opposite directions. So from here we can see that it is a anti-addition, right? Now we will see the mechanism. So when we try to draw the mechanism, reaction is always proceeding via cyclohalonium ion. So first we take an alkene. So this is a alkene, right? And the reagent is X2 in a inert solvent. We know that. So let's write X2 in explicit manner. So this is X2. Now how the attack takes place? This double bond gets attached with this X and another X gets away. So what we obtain is the cyclic intermediate, that is this one, and this one remains as it is, and this bond and this bond forms with the X plus, right? Now we know that we are left with a X minus, because here were the two electrons which being deposited on the X atom. So now what happens? Backside attack takes place, that is SN2, and this one attacks this carbon and this opens up and this positive charge gets neutralized. So ultimately the product which is being obtained is alkane with substitution of two halides, right? So this is the product. So this product is anti-addition product, and also it is known as vicinal dihalide. Okay, and this one is cyclic halonium ion. Now we will see evidences that the addition is anti and it is formed by cyclic bromonium ion. Now see, here we take Z-but2-ene. When it reacts, it gives these two products which are active variety, that is enantiomeric, and forms these two products, and the bromines are placed anti. Similarly, if E-but2-ene is being reacted with bromine in CHCl4, then again the mesovariety is obtained and the two bromines are anti to each other. And to prove that it proceeds via bromonium ion, we have reacted this one. These rings are known as adamantane. So these are joined by a double bond when bromine is being added. So this is the intermediate which can be isolated. Okay. Now we see two examples. First one is this one. Here on adding the bromine, that is Br2, we obtain here and here, that is anti-product. This one will be Br2, right? This one will be Br2 and this one will be also Br2 addition, right? And in this case, see, here is the double bond. So on adding this Br2 at low temperature, we get this anti-product. Now we will see one thing, that is bromine addition is a test for unsaturation, we know that. So bromine is an organic solvent and reddish brown in color. On being added to a double bond, it becomes colorless. So there is a drastic change in color. So it is useful as well as easy to detect the color change. So used to detect the presence of unsaturation is an organic compound and it is known as bromine test. Now color may also change due to the substitution on activated aromatic nucleus. So then we cannot judge whether it is due to the unsaturation or due to the aromatic ring. So let us see the exception here. See this one. This is an aromatic ring with NH2 in it. Okay, and when we add bromine, then the product is like this. That is, this is NH2. Here is a substitution with bromine to give bromide Br minus. So here the color changes to colorless. So we cannot judge whether it is due to the unsaturation or due to the substitution. Another example is that this one, if we take phenol OH and then we add Br2, then the product obtained is like this: Br, OH, Br, and here also in the para position Br plus H, Br, right. Now see this one. This reaction shows that after being added in antiposition on adding sodium iodide in acetone or adding zinc, there is a formation of alkene again. So there is a dehalogenation, right. So how this occurs? This occurs through E2 pathway, that is bimolecular elimination. Now see, let us draw it like this in Newman projection. Now how to draw in Newman projection is being already told. So I will give the link in the description box of that video as well as the I button present above this video. You can watch it. So this is represented in this way, first carbon, and this second carbon is being represented as this way. Okay. Now if I minus is being used from NaI, then this I minus attacks this bromine. This bromine gives up here in the double bond and this bromine gets away, and ultimately the product is this one, right. And this other products which are left behind is IBr plus Br minus, right. This IBr on getting another I minus forms I2 plus Br minus. Okay. Now if we consider for zinc, okay, if we consider for zinc, then the mechanism is slightly different. In that case, we consider it as like this: CH3, H, here is our bromine in the top, and here is our bromine in the down portion, and this side is CH3 and this side is hydrogen. So when we give zinc to it, then the zinc attacks the bromine here, this bromine gets up here and this is released. So we get ultimately the product which is shown as well as Z in Br2. These are the two side products. So for this case these are the side products, and for this case this is the side product, and the mechanism is same for both them, that is E2 elimination, right. Here one must be CH3 in this carbon and here one must be CH3 in this carbon. So ultimately we get an E alkene. Okay. Now we see a function of this, that is, here we have known about halogenation, then now we have come about dehalogenation. So, what it indicates that this consecutive procedures can be used for protection of double bond, right? Protection of double bond. Now, if I show an example for which it can be used, it may be like this, that is CH2, CH, CH2H, and we require to oxidize this CH2H into CH2 double bond CH, COH. So, if we try to oxidize directly, then the double bond will also get oxidized. So, what is the method? Let us see. If we react it with Br2 CCl4, then ultimately we obtain CH2 Br, CH, Br and CH2OH. Thus, we see here that our double bond is now being protected and it will not get oxidized if we add an oxidizing agent, right? So, next we add dilute nitric acid. So, on adding, what happens? This part remains as it is, but the other portion gets oxidized. So, this becomes COOH. Now, what we do? We add zinc dust in methanol and we get the product. So, this is how it can be used for protection of double bond. This is the application. Now, we will see what is allylic halogenation. Now, in case of allylic halogenation, there is substitution of a hydrogen from the allylic position. What do we mean by allylic position? The position next to a double bond, that is this position. First position next to a double bond. It may be this position or it may be this position or this or this. Okay. So, now we will see when it occurs. We have to use high temperature, maintenance of low concentration of halogen throughout the reaction. So, these are the two conditions. We have previously also seen that when high temperature is present, the addition reaction does not take place. So, here the substitution, that is allylic halogenation, will take place. Now, how to maintain the low concentration of halogen? This can be only maintained by using, for bromine we will use something different, that is NBS. NBS is N-Bromo Succinimide. Okay. So, this NBS looks like this, that is, it looks like this, NBr, NBr and this one, 2 double bond O. So, this is N-Bromosuccinimide. Okay, N-Bromosuccinimide. Now, one may think that how can this one provide us with Br2? Yeah, it has something which provides it. So, let us read it. It is used to maintain the low concentration of Br2 as it contains Br2 in low concentration as impurity. This is important, which starts halogenation, and the liberated HBr from that reacts with NBS to give Br2 after the reaction. Now, we will see this reaction mechanism. Now, see this one here, this carbon is having 3 hydrogens, one of the hydrogen is being substituted by X, that is halogen. So, we will see the free radical mechanism right now. First, for a free radical chain mechanism, first step is chain initiation. So, in that case, first step is X2 in presence of heat or light produces 2X dot, that is the bond breaks up and this one has 1 electron and this one has 1 electron. The second step is chain propagation. In this case, what happens is the allylic part is being opened up and shown, and this double bond is being present already, plus this X dot produces free radical. How does it produce a free radical? Now this comes here and the hydrogen gives up one electron towards itself and one towards here. So ultimately the product which is formed, the free radical, is this, right, plus HX. Now to it, if we add X2, then again this one will grab this goes here and the electron comes here. So ultimately we obtain the product which is CXC double bond C, right, and what are we left with is one X dot. So this is how the mechanism occurs, and chain terminates if this X dot reacts with H dot or any of the following other free radicals present in the mechanism, and then the reaction stops. So these allyl free radical is highly stabilized through resonance, and consequently its formation is associated with low energy of activation. So we have to remember this. Now let us see one example. Here on adding NBS there is a allylic halogenation. Now this case we see that there is a mixture of product. Now one may think that here there must be one addition of chlorine in the double bond or substitution of the chlorine in the allylic position, but actually here only substitution in the allylic position takes place, followed by rearrangement in one of the cases, and this results in the mixture of product. So we will see the mechanism first. See this one. This can be written as this one, right? So on adding chlorine, H nu, we get a radical which looks like this somewhat. It loses an electron and it looks like this. So this undergoes resonance to form this kind of radical. And here comes the double bond. How does it take place? Now this radical comes here and this electron from here is donated here and another comes here. So ultimately here there is a double bond formation and one of the unpaired electron is present here. So now on adding X2 on both of the cases, what we get is these two products. This one here, one chlorine, and the double bond remains as it is. Another one double bond gets rearranged and comes here, and this one is our product. So these are the two mixture of products due to the movement of the electron, single electron. Now we will see this one. Now just see here that here the double bond is being present and we add bromine. So on adding bromine there should two bromines in the entire position, but it is not so. Here there is a second step where we have added the base. So the mechanism is somewhat different. So let us see this one, how it occurs. So first we draw it by adding the bromine. So on adding first Br2 CHCl3, we get this kind of structure. COOH, H, Br here, another Br here, and this one is hydrogen and this one is methyl. Now what we do, since base is present, base primary work of base is to abstract proton, that is to obtain the proton, right? So it will try to obtain the proton. So what, in which carbon should it abstract the proton? This one, because here COH is present. So this one will be loosely bound and easily abstractable. So now we need to just reshuffle the diagram. So we redraw it as this, that is H is taken above, Br is here, that is this carbon is being rotated in this direction, and here is the COOH and here it is MAHBr. Now on adding the base, what will it do? It will abstract the proton and it will give up this one, and this one will be removed. So ultimately the product which is obtained is, in this carbon there is COH as well as the bromine, and here it will be methyl and hydrogen and a double bond in between. So this is how this reaction occurs. Now on further adding sodium in liquid ammonia, then we are going to get a product where there is no bromine. This bromine will be replaced by a hydrogen. So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.